Okay, so today's video is going to be talking about acceleration. Um, Acceleration is defined as the rate of change in velocity. So anytime that we're talking about some quantity being the rate of change, that means that we're dividing by time. So if I'm trying to change this definition into an equation, I got to make sure that time is in my denominator. And a change in velocity, we use the symbol delta to show change, and voila, I end up getting my equation for acceleration. And this is the second equation that you'll see in your reference tables, that it's a change in velocity divided by time. Now, if I want to talk about the unit of acceleration, velocity has the unit of a meter per second. And then time has got the unit of seconds. So what we end up getting is a meter per second, sometimes written like you see over here. Or if I copy, change, flip this is equal to a meter per second divided by seconds, or seconds over 1. And if I copy, change, flip that's a meter per second times 1 over second. So this is end up equaling a meter per second squared. So that's where this comes from. A way that we can read this is a meter per second for every 1 second of time. Now, since velocity is a vector, being a quantity with both magnitude and direction, so how fast and in which way is it moving, acceleration also is a vector quantity. So acceleration also has a magnitude. How much is it changing its velocity, and in what direction is that velocity changing? So let's just take a look at an example and you get a better idea of the meter per second per second. So let's say an object is accelerating at 5 meters per second for every 1 second of time. Then that means that at a time equal to 1 second, the velocity is going to be equal to 5 meters per second. So it gained 5 meters per second in that 1 second. At 2 seconds, the velocity is going to be equal to 10 meters per second. I took the original 5 and I added 5 more to get us the 10 meters per second. And then we can do this one more time. At 3 seconds, the velocity is going to be equal to 15 meters per second. So as much time goes on as the problem, let's run, then it's going to gain 5 meters per second every second of time. So let's take a little closer look at this equation. So A equals delta V over T. Okay, and so delta, anytime that we have delta, that is the last minus the first, or we use the subscripts F for final minus V sub I for V initial. So this is the final velocity minus the initial velocity. If I plug this in, this Vf minus Vi in for delta V, I get A equals Vf minus Vi over T. And what I'm going to do is I'm going to manipulate this equation to get Vf. I want to isolate Vf and get Vf by itself. So I'm going to first multiply both sides by T by cross multiplying. So I multiply this side by T, then I multiply that side by T, then my T's cancel out over here. So I have T times A equals Vf minus Vi. Then I'm going to add my Vi. And so these cancel out over here. And so I get Vf on this side equals T times A plus Vi. Now I'm just going to kind of rearrange this to make it look like your reference tables. So I have Vf equaling Vi plus AT. And this ends up being the third of your equations in your reference tables. Now notice that it was nothing more than this equation up here, just it's solved for Vf. So most of the time we will use this. However, there's one situation where we end up really wanting to talk about that. And that's when we take a look at a velocity versus time graph. So let's just take any velocity versus time. Let's say we have something that's a linear relationship. The slope of this line is a change in velocity divided by a change in time. Okay, this is your rise, a delta v, and this is your run, a delta t. So in other words, the slope of your velocity time graph represents the acceleration. So the slope represents the acceleration. So now we have the slope of this graph being the acceleration, and we have the slope of our position time graph. Let's go back to our previous model. Say we have something that's squared relationship between position and time. The slope of this graph, if you recall, is the velocity. So we have the slope of velocity time being the acceleration, the slope of position time being our velocity. So let's take a look at a quantitative example. So let's say a car starts with an initial velocity of negative 5 meters per second, and at the end of 15 seconds, the car's velocity is positive 25 meters per second. We want to know the car's acceleration. So all good problem solving starts off by listing what you are given. So I was told that the initial velocity here is minus 5 meters per second, that the time is 15 seconds, and the final velocity is a plus 25 meters per second. And I'm asked for the acceleration. So what I'm going to do is I'm going to put a little question mark next to acceleration just to let me know that that's what I'm solving for. So I can use either it looking like this, or I can use it looking like this. And so since this one is actually already solved for acceleration, I'm going to use this equation. So my acceleration is a final velocity minus an initial velocity divided by time. So my final velocity is a positive 25 meters per second, and I'm going to subtract a negative 5 meters per second, and then divide that by my time, which is 15 seconds. So if I take my 25 and I subtract, that's nothing more than adding the positive. So this is 30 divided by 15, or 2 meters per second squared. And we'll put a little positive there just to kind of show that, yes, we understand that it's a positive acceleration. Therefore, its acceleration is in the positive direction. If we take a look at the follow-up to that, if a second car has the same acceleration, so the acceleration has to be a positive 2 meters per second, we want to know what its final speed is if it begins at rest. So if you see something say it begins at rest, that tells us the initial velocity is 0, and we want to know how fast it will going. So VF is our question mark after a time of 4 seconds. So I'm actually going to choose this here once again because it's just like A was already solved for in the first example, VF is already solved for here. So I have VF equaling VI plus AT, and VI is 0, so I can cancel that off right off the bat. And so the final velocity is the acceleration of plus 2 meters per second squared times 4 seconds. So 2 times 4 is 8. We get a positive 8 meters per second. So now notice we can kind of use this as our definition before, that if I say the acceleration is 2 meters per second squared, what I mean by that is that it changes its speed by 2 meters per second for every 1 second of time that goes by. So after 4 seconds, and it starts from rest, the object's going a positive 8 meters per second. So in this case, the acceleration and the velocity are in the same direction. And I'll actually just put a box or circle around my final answers. So let's say I have a car and it's heading in what I want to call the positive direction. So I'm going to say to the right is positive. And I will also want, so the velocity is to the right. And what would happen if the acceleration is also positive? Well, what I expect to happen is that this object is going to get faster. So if I show as a motion diagram, that we would expect the dots to get further and further apart. Therefore, the object is speeding up. If, once again, let's call to the right positive, let's say my velocity for my car is to the right, so my velocity is to the right, but my acceleration is to the left. What this object would be doing is slowing down. So if it's starting off at a big speed, dots being further apart, those dots are going to get closer and closer and closer until the object stops. Okay? Now, if we are talking about a fan car, what would happen after the stopping point is what we'll discuss later on in the unit. But for right now, the important thing here is that when the velocity vector and the acceleration vector go in opposite directions, we get slowing down. And when the velocity vector and the acceleration vector are in the same direction, we end up getting a car that's speeding up. Okay, we'll follow up further with that, as I said, later on in the year. But this kind of incorporates our motion diagram, our velocity and acceleration vectors, and also choosing what direction you want to call positive. That choice is up to you, although it will be much easier if you talk about the whatever direction the object's moving to be the positive direction. So that's all for now. We'll talk more accelerations later. Have a good night, and we'll see you then. Bye.